Welcome to the second segment of NatureServe's data use training. This tutorial covers things to be considered when using and interpreting NatureServe data with the focus on how we prioritize and delineate species and ecosystems. If you have not yet successfully completed segment 1, including the quiz, please do so before taking this segment. If you have, congratulations. Please continue. In the next two segments, we will provide you with information you need to know in order to use NatureServe data.
NatureServe data is useful for any activity that requires information on the location, status, and conservation needs of species and ecosystems. Data provided by NatureServe have many potential uses. Just a few examples include avoiding and minimizing impacts of development on rare species, informing and guiding resource managers, and informing conservation decisions. Let's start with this question. What do you receive when you get data from NatureServe? Or in our jargon, what elements of biodiversity are included in the data? Our member programs do not track, that is, map the locations of all species and ecosystems. Species must be imperiled or vulnerable to be included, and ecological communities must be exemplary. I am not going to define exemplary ecological communities here. Not all programs track them, and they typically are not included in the aggregated data that NatureServe distributes. But you should be aware that individual programs in our network may have such data available. So a species has to be imperiled or vulnerable for its populations to be tracked by a program in our network. One way for a species to qualify is to be rare. For example, it may be found in only one small area, or distributed widely but only in very specific habitats, or it may always exist in small numbers wherever it is found. Some species are rare in all three senses, such as a plant that occurs only as a small population on calcareous cliffs on one mountain. Keep in mind, though, that rare species can be locally abundant. These yellow flowers are the only population of smooth burr marigold currently known to occur in New Hampshire, qualifying them as being imperiled in the state. On this one riverbank, however, they're clearly doing very well. Rarity is not the only thing that can qualify a species for tracking by our member programs. Other considerations are known threats to the species and known drops in population size. For example, the northern population of the bog turtle has declined by at least 50% over the last 20 years. The decline is due primarily to habitat loss, including degradation and fragmentation, combined with excessive and illegal collecting for the pet trade. Even if population sizes are still fairly large, as long as collection and habitat loss continue, this species will be considered to be imperiled or vulnerable. Member programs assess these three factors, rarity, threats, and trends, and calculate for each species a conservation status or rank on a scale of 1 to 5, where 1 means critically imperiled and 5 means secure. This 1 to 5 ranking can be applied at several geographic scales. Here it is shown at the subnational or state-province scale, and the numerical rank is preceded by an S for subnational. We also apply the ranks at a range-wide or global scale, in which case the ranks are preceded by a G for global. The species that programs track are those that have a status of S1 to S3. They are imperiled or vulnerable. The programs also maintain historical records of extirpated and possibly extirpated species. You can see that in Vermont, up near the very edge of its range, Fowler's toads are critically imperiled, but in most of their range, they are in good shape. S4, or S5. So Fowler's toad, looking at its global distribution, is assigned a G5, or secure status, though its rank is S1, critically imperiled, in Vermont. Another way to say this is that Fowler's toad is in serious danger of being extirpated from Vermont, but is not at risk of extinction as a species. You might wonder why conservation efforts would focus on populations of species that are globally secure. One reason is the unique genetic traits of edge-of-range populations, and another is the cultural values of maintaining species that have traditionally occurred in a state or province and are part of that jurisdiction's flora or fauna. So what you see here is typical of many species. They will be tracked by some programs when they are at risk within that state or province. Other programs may manage some information about them, but they will not track them because they are abundant in that jurisdiction. On the other hand, globally imperiled species are, by definition, imperiled throughout their range, and will generally be tracked in every jurisdiction in which they occur. Let's look for a moment at the difference between NatureServe's conservation status and legal statuses in the United States and Canada. Most people are familiar with the species designations within their jurisdictions. Often, these confer at least some legal protection for the listed species. Both national governments and state or provincial governments list species based on a different set of criteria than those used by our member programs to determine conservation status. The listing criteria tend to be complex, and the process is usually much slower than assigning conservation status values. So, relatively few species have been evaluated for listing status. Based on conservation status assessments, NatureServe considers more than 16,700 taxa to be at risk, that is, imperiled or vulnerable, throughout their range. Of these, only about 13% have any federal level legal status, and most at-risk species have no state or provincial level legal status. Member programs typically focus on species in certain taxonomic groups: vertebrates, vascular plants, and some invertebrate groups such as mussels and butterflies. But there are large groups of species where we just don't know enough about them to know how much at risk they are. For these groups, there are no state or province-wide inventories, and very little is usually known about abundance, threats, or trends. Exceptions are the species in these groups that do have legal status. They are usually high priority. So far, we've been talking about elements, entire species. Now let's look at occurrences or populations of species. Given that a certain species is tracked, for example, a critically imperiled species of butterfly, will a member program create a record for every sighting of that species? The answer is no. Programs only track sightings that meet certain standards. The sighting has to occur in appropriate habitat at the appropriate time of year, and usually it has to be a naturally occurring instance. If a sighting meets these conditions, it can be entered into the Natural Heritage Database as an element occurrence, or EO. An element occurrence is an area of land or water where a species is or was present. An important part of the definition is that an EO should have practical conservation value. The goal is not to track individual plants or animals, but rather areas that support populations. Consider which of these sightings would qualify as an EO. Egg masses of a rare salamander? Yes. Good habitat, right time of year. How about a rare orchid in a bog? Yes, absolutely. How about a rare warbler appearing at a bird feeder in winter? No. Wrong time of year for a warbler. Also, if that bird feeder were not there, that one stray bird might be lost, but the species would not be affected, so the bird feeder sighting does not have practical conservation value. How about a pile of freshwater mussel shells, including those of a rare species, recently eaten by a muskrat? Yes, that could be an EO. Recent mussel shells would be a strong indication that a rare species is in the area in appropriate habitat. Observations of dead plants and animals do count. A peregrine falcon seen flying over a Walmart store. That does not seem to give us enough information, does it? Because birds are so mobile, many sightings occur in areas that do not have conservation value for the species. For birds, typically we want to have evidence of breeding activity to consider a sighting an EO. So no, the Walmart sighting would not be mapped as an element occurrence. Now is probably a good time to talk about the relationship of observations to EO methodology. An observation is the presence, historical presence, or confirmed absence of species or ecological elements in an area, indicated by the collection of information. You can see that this definition is quite general. It encompasses a broad range of things that may be useful for many purposes. The warbler at the bird feeder in the previous slide's example is certainly an observation, and it may be very important data for some purposes, even though it is not used to create an EO. The main point is that not all observations are an appropriate basis for an EO, but all EOs do have observations at their root. In this presentation, I'm focusing on EOs as they constitute the vast majority of NatureServe's spatial data. However, you should be aware that NatureServe is increasingly incorporating observations into its dataset for species. Observation data may be useful in conjunction with EO data, depending on the nature of the question you're trying to answer. In terms of EO methodology, one or more appropriate observations are used to create what we call a source feature. A source feature is just the observation or observations plus an area describing any uncertainty related to the actual location of the sighting, what we call buffering. The locational uncertainty can be negligible if the location is known with high precision. The source features, that is the observations plus any spatial uncertainty, are then usually grouped into element occurrences. There are exceptions to this grouping, in that a few programs map each observation or source feature as a single EO. This is done primarily with extremely mobile animal species, where making the decisions about grouping can be difficult. So how do we decide which source features should get lumped together into one EO and which should constitute distinct EOs? Let's say a program already has an EO for a particular species. The decision of whether a new sighting nearby is an update to that existing EO or an entirely new EO is based on how likely it is that individuals, or propagules, are likely to be exchanged between the two. So we look at two things, proximity and any obstacles besides just distance to the exchange or dispersal of propagules. Here is a depiction of the process of evaluating a new sighting. First, is it an element occurrence, based on specifications that include appropriate habitat and time of year for that species? Then, if it is an element occurrence, how widely separated are the observations? Suppose in this example that the blob on the left represents an existing EO, and the blobs on the right represent new observations. If the separation distance is easily traveled by this species, then these observations would be treated as a single EO. Besides absolute distance, the type of terrain is considered. Are there barriers, such as mountains or rivers, that would make these areas act as separate populations, rather than subareas of one population. It is possible in the example on the right, given the barrier, that the blue area would be considered part of the larger blob on the left, while the green area would be a separate EO. These decisions are important because many analyses involve counting element occurrences. For example, when asking how many known populations, or EOs, of a rare species are on protected land. You don't usually have to worry about whether an EO is new or updated. Our member programs have made that decision based on species-specific guidelines, or decision trees. But you do have to be aware of something called sub-EOs. These may be areas important for different activities of the species, such as feeding versus breeding, or different habitat conditions within a single EO, or just geographically separated areas within the EO. The thing to be aware of is that there will be separate records in the database for sub-EOs. Sub-EOs are important whenever you need to count the number of EOs in a given area. To avoid double counting, you need to check the field in the attribute table that identifies EOs as sub-EOs. Back to our EO blob. Here's what sub-EOs might look like. The big blob could be a single principal EO, with two sub-EOs embedded within it, each representing, for example, a den site. Every element occurrence has two main pieces, a database record in tabular format and a mapped location. The attribute tables of natural heritage records include many fields from the database. Some of them are element-level data, such as how at risk the species is. Many of them are occurrence-level data, such as when it was first and last observed at this location, and written directions to the site. The tabular data also includes metadata about the data itself, such as who observed it, or whether it came from a specimen label versus a field survey. Much of this training is devoted to drawing your attention to a subset of the database fields, the ones that are especially important to think about when analyzing the data. The mapped component of natural heritage data also has a lot of information embedded in it, and there is a piece of natural heritage history you should be aware of to understand the shapes you'll see. Currently, natural heritage data are all mapped as polygons, including circular and linear polygons. Before GIS, though, EOs were recorded just as a point, using lat-long coordinates, such as illustrated in the bottom inset. Then, points were converted to circular polygons, or buffered, with different diameters depending on the degree of precision of those points. For example, a low-precision point, like one based on an herbarium specimen, that just said Town of Andover, would have been converted to a really big circle. More recently, member programs are working to convert circular polygons to ones that better show the actual known footprint of the observation, such as shown in the top inset. I'll give a more detailed example next, but be aware that both within and between states or provinces, you will see a mix of old-style and newer polygons. Here is an example contrasting old-style and newer mapping techniques in adjacent states or provinces. In the area on the left, source features, remember that is the occupied habitat where the species was observed, have been mapped as polygons. On the right, observations have been mapped as points when the location information was exact, or as large circles to reflect a high degree of uncertainty in the location of the observation. This situation could occur within a single state or province, as well as across borders. For example, with older, less precise records in more remote areas. The problem is just more prevalent when you are dealing with states or provinces with different levels of resources and sometimes differing internal priorities. the level of survey among programs can be very different. Imagine the step of deciding which of these observations should be grouped into the same EO. Separation distance criteria, based in part on suitable habitat, are hard to apply with imprecise observations, such as those large circles on the right. It is often desirable to not include the oldest, least precise records when counting EOs. Here is a great example from a small national park in Ontario. On the left, you see the old-style circles, in this case representing source features for the common hop tree. If we can ascertain that the observation was made within the park, one easy way to refine these big circles would be to simply clip them to the park boundaries. In this case, the Ontario program was able to go much further in refining these polygons, as shown on the right. Given the small area, these source features would likely be grouped into one element occurrence. Next, I'll use a site-specific example to illustrate some important features of NatureServe data and to teach you more about how you can use the data. Imagine that your task is to evaluate a site where there is a proposal to construct a telecommunications tower. If the tower is going to be put on the top of Nuds Hill, how can you use NatureServe data to evaluate the site? The black border, by the way, shows the bounds of the property where the tower will be installed. Data you receive from NatureServe might look like this. You can use this information to evaluate potential impacts of the proposed tower based on what rare elements have been observed in the area. The NatureServe data shows occurrences of 3 plants, shown in orange, and 3 animals, shown in red. If we focus on the Blandings turtle record from the example, it's mapped as a straight line along a road. It is not very likely that a biologist followed one turtle as it traveled slowly down this road. What we're seeing here is a point observation, but with some uncertainty about just where the observation occurred. Unfortunately, all too many turtle records are based on a dead turtle at the side of the road, and that's the situation here. A quick note on why this is an EO, even though pavement is not appropriate habitat. Unlike birds, turtles do not usually travel far from their home base, so almost any observation of a rare turtle would be considered to be an EO. To get back to locational uncertainty, if this turtle sighting were a written report that said, opposite the pond near the school, with no map provided, the person putting the record on the map would usually not be able to just put a point at the observation site. The sighting itself was a single point in space, but when an EO is mapped, locational uncertainty is added until the mapped shape includes the range of locations where a sighting could have occurred. Notice that what the mapper did not do is try to guess where the habitat for this dead turtle might have been located and map that, rather than the known location where the observation actually was made. Remember that actual locations are at the root of EOs. Now let's look at the ginseng, which is mapped as a very small circle inside the larger circle. Without even checking the dates in the tabular data, would you guess that this is a recent sighting or an old specimen? It pretty much has to be a recent GPS point. There are no landmarks to explain the exact location, yet there is no locational uncertainty. GPS units make our mapping much more accurate, but a lot of information in NatureServe's database was not collected with GPS. 2 more examples, a plant and a bird, both mapped as a large circle centered on a hill. Both could be a vague report of a single sighting that just refers to the name of the hill, and most of the mapped area could be locational uncertainty. Or it could be that sightings have occurred in multiple locations on the hill. In fact, it is possible, but unlikely given the perfect circular shape, that the species could have been sighted throughout the mapped area. The circular shape strongly suggests high locational uncertainty, but you need to look at the tabular data, particularly at the precision or representational accuracy field. Representational accuracy refers to the proportion of the area that was actually observed to be occupied. If this has high accuracy, then observations occurred throughout most of the mapped area. If low, most of that big area is due to locational uncertainty. This is important in that a big, low accuracy occurrence can be misleading in many types of analyses, whereas a large, high accuracy occurrence will not be. For example, if you want to know how many EOs are in a county, should big, imprecise EOs that just barely clip the county count? The Arethusa, which is an orchid, has a nice squiggly mapped shape. This could have come from someone with a GPS carefully walking the bounds of a population, but there's another possibility. If you check the metadata, you may find out that the shape was copied from the National Wetlands Inventory. There could have been a single sighting of this orchid that was noted as occurring within the wetland. Again, in the tabular data, there is a field called representational accuracy that, when it has been calculated, will tell approximately in what proportion of the mapped area the sighting occurred. There is also a text field describing the size of the population. Survey effort is another very important factor to consider when interpreting NatureServe data. Most areas have either not been inventoried or not inventoried for all elements. For example, they may have been searched by a birder, but not by a botanist. Because of this, it's important to understand that the absence of a NatureServe record does not mean that no at-risk elements are present. On the other hand, the presence of one rare element may indicate that the habitat is unusual, and that other rare elements may be present as well, but are yet to be documented. Here is a real-life example of survey effort and how it affects the mapping of EOs. These are source features for a rare bird, Bicknell's thrush, and they are all, curiously, in a nice line. The survey was done by hiking the Appalachian Trail during breeding season, playing territorial calls and listening for responses. Usually, the type and amount of survey effort is not this obvious, but remember that it is rare for surveys not to be influenced by logistics, proximity to roads, trails, universities, inevitably influences the degree to which the area will have been surveyed.
Congratulations! You've successfully completed the second segment of NatureServe's data use training that focused on the methods we use to prioritize and map species and ecosystems. Next, please click on the Take the Quiz link on the tutorial page. The quiz includes questions on the material that was just covered. You must take this quiz to earn credit for completing this segment of the training and move on to segment 3 of the training.